Hey, what's going on YouTube? So, welcome to the stream. My name is John. I am a former math major and turned iOS engineer. I've been working at Google and other large tech companies for the last 10 years. And now I'm reviving my love of math. So, we are here on week one practicing calculus. So, I'm going to relearn calculus here with you all. And hopefully we'll have some fun along the way. So we're going to solve every calculus problem ever. Right now I can show you today's stream. I'm going to be introducing the books that we're going to be choosing to work through. These are the ones I have now. I'm sure I'm going to get more along the way. But these are the ones that I happen to have at the moment. I'll talk about what I like about some of them or why I chose these. And we'll start introducing some of the very basics for calculus. So I think that the best place to start with calculus is going to be functions. As simple as that is, there really is this interesting zoo of different types of functions in calculus. So you have these like smooth functions or these like really erratic, strange, sharp, angular functions. And so, yeah, we're going to start to understand the zoo of functions beginning today in the stream. And it works well because one of my viewers recently asked in the comment section, shout out to Patricia, about a great question about functions. So we're going to get to that today. I promise I'm not ignoring your questions. I'm just saving it for a future video, usually. Okay, so let's get the iPad up on screen. I thought it was working. Why isn't it working? Let's get it working. Let's get it working. What's up? All right, window capture. Cool. All right, so I'm a math hobbyist, mathhobbyist.com, etc. These are the books that we're going to work through. I created a little table of contents. We're going to solve every calculus problem. This is kind of a joke, 11225 to until, like, when are we going to be done with this? It's going to be a while, probably, but maybe I'll create a different page and, like, close out some of these table of contents, probably when we hit the limit in this app. But anyway, so these are the books that I have at the moment. We're going to do Taalman and Cohn. We're going to do Rosenlicht. We're going to do Tenenbaum and Pollard. And we're going to do Gamelin and Green. So my notation here is, if you haven't been watching the linear algebra series, that's where I introduced this. My notation is easy. This is a very American or Western, at least, bias, that like red is hard, green is easy. I know that in other cultures that is not the color coding, the cultural standard color coding, but it's what I'm used to, so it's what I'm going to choose. So I do want to make sure I write those in because it's not obvious for everybody. Okay, so green is easy, yellow is medium, red is hard. I'm probably going to change some of these colors as we go. I know that there are many harder books and there are many easier books as well as these that I've chosen. In particular, I think Rosenlicht, I could argue that one is a hard book. I used it in an upper division calculus, quote-unquote, class in college. And it was a fairly hard class, but it's not as intense as, it's still an undergraduate book. It's not a graduate level calculus book. So I keep using the word calculus, and I will start to define the difference between calculus versus analysis. But we've got a lot of interesting things to talk about with calculus. I'm using the word very broadly. And yeah, let's just get going. So, Taalman and Cohn. This matches exactly the pattern that I introduced in the last video, or in one of my first videos. This matches the pattern that I claim, that the hardest books are tiny, the scariest books are tiny, or some scary books are tiny is really more accurate. This one, fairly large, fairly friendly, undergraduate, first semester calculus. But it's a beautiful book. This is a lovely book. I highly recommend this book for everybody. So it is a good alternative to Stewart's calculus book, which is the most famous calculus book. It's got a violin on the cover, at least the edition I used, and many editions did. Stewart Calculus is great. It's very good for a lot of good reasons. It's a great book. But it and others, like, I'm blanking right now on the name of another one that's really famous, but a lot of math books at the high school and, like, math for non-majors university courses, they often have, like, a lot of marginalia. They have, like, a lot of diagrams and little historical blurbs about mathematicians to keep your interest going. In number theory, I have one that I liked in the course that I took in college, but now I'm rereading it and I'm like, there's too much marginalia. There's too much boring, annoying stuff getting in the way of understanding the mathematics. So that's just a thing. Like, when a math book is written for non-mathematicians, there's often a lot of historical marginalia. There's a lot more pictures, and that's great in a lot of ways, but I do think that stuff, like all the cartoons, can really get in the way of understanding math. And this book is just lovely. It's wonderful. It has color. It's not that it's not colorful. It does use some tasteful amount of color. There's like some nice blues. There's some nice light browns. It's not like a black and white hardcore pure math textbook, but it is clear. There's no marginalia. There's no distracting, unnecessary stuff. It is just relatively straight to the point, and it's presented in a modern mathematical organizational style, sort of like the Bourbaki style. Theorem 2.12, the chain rule. Theorem written in like a nice colorful box, and then a proof. There are proofs in this book, and it is written like in the style of a pure math textbook with the audience of non-mathematicians in addition to math majors. So, like, I really like this book. It's a great book from what I've seen so far. I was tutoring a student. I had a PDF. I found a PDF online of it, and I was just like, I gotta get that book. It's really nice. So, yeah. Briefly, I am available for tutoring if anybody wants a tutor. Let's move on. So, Taalman and Cohn, we're just following the pattern. We're still seeing the same pattern. This is first semester calculus. It's designed for a 3-semester course in calculus, and if you're an engineer, this may be your only experience with calculus. You don't have to take any further calculus courses besides Calc 1, 2, and 3, at least in the US. That's how it's structured. If you're an engineer, you probably do need to also maybe take a full dedicated course on differential equations. Differential equations is one of the big motivating reasons to learn calculus. Differential equations come up in the real world all the time, like the heat equation, or if you want to understand like populations. I don't know. I'm not an applied mathematician. So I hope that if I work through this book, I'm going to get more appreciation for differential equations and how calculus is useful in the real world to understand how far we can throw baseballs and stuff, or build nuclear bombs or whatever. So one thing is calculus is tremendously useful for physics. Physics is one of the biggest motivating reasons that we invented and created calculus. It's to understand nature, it's to understand the motion of the planets around, in the night sky. It's so that we could understand how far we can throw baseballs, or how fast an apple hits the ground, or whatever. And so someday, I don't know if it's in the calculus series of videos, of practice sessions, or if it's in its own applications series of videos. All of these are practice sessions, by the way, if it's not obvious. But we will probably study some physics, just straight up physics. And here's a couple of great books that are super calculus related. Like, you need to know differential equations if you want to learn quantum mechanics. I worked through this book in college, at least the first half of it, in a upper division second quantum course. It was lovely. I really liked it. To understand quantum mechanics, you need to understand the Schrodinger equation, which is a differential equation. So there is one example where calculus is useful in the real world to understand the bizarre nature of reality that is quantum mechanics. I thought about taking this course. I was enrolled in it, but then I dropped it to finish a philosophy minor instead of a physics minor. I still think that was the right choice. But this is a scary-ass book. This is Jackson. This is like upper division, or not upper division. That is graduate electricity and magnetism. Calculus is amazingly useful to understand electricity and magnetism. Cool. So let's keep going. Someday we'll do some physics here on this channel if this picks up an audience and people enjoy it. Any questions? No. All right. So following the pattern, as the books get harder, they get tinier, right? That's as they get smaller, it should raise your alarm bells. Like, this book is as thick, it has as many pages, or just like slightly fewer pages than the Taalman book, but it's smaller. It's I can hold it like this, whereas the other book is like that or something. So that's matching so far, but this is still useful in the real world. So maybe it's not as scary as this book, which this book is much scarier. Look at it. It's tiny in comparison. It was like $20, I think, or $15. It's a Dover book. Dover books are incredible. Go get it. Go buy every Dover book if you can afford it. But the topics get scarier. We're talking about metric spaces. There's a whole chapter on continuous functions. And this doesn't even get into it. I just realized I do have a much scarier book. So these two are about as scary as each other. Introduction to Analysis, Introduction to Topology. So first, analysis is mathematicians speak to say theoretical calculus. This is proof-based theoretical calculus. Proving everything with epsilon delta proofs, etc., etc. Beautiful. Everything gets rigorous. Calculus was really built by Newton and Leibniz on pretty shaky grounds. It was kind of like we defined everything in terms of these infinitesimals, and there's the smallest possible number greater than 0 or something. I don't know. Calculus was defined on very shaky grounds, and then like 100 years later, some engineers tried to tried to create some really interesting math, and mathematicians were like, no, that doesn't make any dang sense. And the engineers were like, but it works. And so the mathematicians were like, we got to go back to the drawing board. We got to figure out why this stuff works. Let's put everything on firm ground. So this is theoretical calculus. And so we will be comparing and contrasting some definitions from a first course in calculus with calculus for math majors. This is about as scary. It's like the same size. That matches really well. So I put this one as red, but I think that the difficulty level is going to be the same as the other one. But this one's even more abstract. It's even further away from the real world. Topology is... It's kind of a stretch to put it in the calculus series, but I think it makes sense. Topology is kind of like calculus when you remove the concept of distance. When you talk about shapes, without talking about how far apart 2 points are. So it's kind of also geometry. It is just as much geometry as it is calculus. But there's a famous joke that to a topologist, a coffee mug is literally the same shape as a donut. And when they're drinking coffee and eating a donut at the same time, they can't tell which one to pick up, or something like that. That they see the two, they're so interlinked that they have to have a donut every time that they have coffee. I don't know where I'm going with that. But the reason is that they both have exactly one hole, and everything else can be reshaped. You can just squish the rest of it like Play-Doh. You can just reshape this coffee mug, if it were made of Play-Doh, into a donut, into a torus. So, yeah, that's interesting. So, in some sense, like a space with one hole in it is fundamentally different than a space that has 2 holes in it, or a space that has no holes in it, like a ball. And yeah, so we're going to learn a little bit about that. And then, I forgot, I do have a terrifying book. Where is it? So we created this fancy word, analysis. Ooh, analysis. That is pretentious speak for theoretical calculus. But then as the books get harder, they sound easier, the titles sound easier, and they get smaller. So we're back to calling it calculus again. Here's Spivak, Calculus on Manifolds. This book is scary as hell. This is a scary book, and it's tiny. Look, oh my god, it is so tiny. Compare that with this one, which is also pretty scary, honestly, but like you can just tell by the number of pages that this one's going to be much harder, which is ironic and funny. So I wanted to share that with you all. The pattern keeps holding true again and again. Beware of the small math books. Okay, so there's a little bit of lecture or flavor, one might say, and let's get into it. A viewer asked last time, a Q&A, a viewer asked, I should really ask it exactly, precisely how they phrased it. That would be more authentic, more... I wish I were more prepared, but I'm not. They asked... Let me try to find it. They asked, what is the name of an equation that is not a function? like the letter C. So what this viewer, shout out to Patricia, is asking about is, for example, the letter C. What she's referring to is the fact that, let's put the iPad back on screen. So the letter C does not satisfy what we call the vertical line test. If you take a vertical line, does it cross this this shape or this equation in two places? In this case, yes, it crosses at two different y points. So for this one x value, there are two y values. That means that this is not a function of x. It's kind of this quantum thing where it may be one, or it may be the other, or it may be both, or etc. So there's not a function, there's not a single rule that will tell you that x maps to y1, because x also maps to y2. So that's a great question. What is the name of something like this? Well, there's a couple of ways to answer that. One is we can treat the example that you gave as a function of y instead of a function of x. Because a function of y does satisfy the line test. So we should start removing the bias of thinking of a vertical line. What matters is that there's only one value for every input. Okay, so in this example that you gave, f of y does always map to exactly one x value. Like when y, when y is 0, maybe x is -2 or something. When y is 2, then x is 2. I don't know. I'm trying to estimate what these tick marks are, distances in this thing. So yeah, you can kind of think of it like if you rotated it 90 degrees, then you could see that the letter C is very similar to a parabola. It's kind of like we're drawing a parabola from 2 points. So that's the beginning of my answer, but we've got more details to fill in here. What precisely is a function? So a function is a rule that maps every input to one output, to one value. So let's get more precise. So what do I mean by a rule? What do I mean by map? What do I mean by input? What do I mean by output? A function f. Sorry, let me pause for 1 second. Because I kind of avoided your question a little bit, and we will get to answering your full question. Here's another example. If we have two C's that are kissing each other, then we have a circle. So maybe this is the equation x squared plus y squared equals 1. In short, what we have here is a graph. this is a graph, and a graph is a set of points, and in this case, x and y are both real numbers with the rule x squared plus y squared equals 1. So this is a set of points. And it doesn't satisfy a vertical line test or a horizontal line test. So it is not a function, it is a graph. It's a collection of points. But it could be thought of as a function on certain, if you restrict it to certain things. Like if you restricted it only to x greater than or equal to 0 and y greater than or equal to 0, then this is a function of x or a function of y. Like if you take only that piece of the circle. If you could also take the top half, and that would be also a function, because there's one y value for every x value. And so what I want to get at here. Oh wait, what am I? Yeah, if you take the top half. So what would it mean to take the top half? That would be saying y greater than or equal to 0. X, y, and r, y greater than or equal to 0, x squared plus y squared equals 1. Okay, this, I think, is still technically rigorous, but there are some problems. Here I'm saying that x and y can be any number in R, and here I'm restricting it to saying x squared and plus y squared equals 1. And here I have this extra restriction that y is greater than or equal to 0. This is still correct. This is still equivalent to restricting this set a little bit further. It doesn't change anything because we know that the only x and y that could solve that equation for a circle, they don't have to be of all of the real numbers. We can take the interval -1 to +1, y greater than or equal to 0, x squared plus y squared equals 1. And here's another way of writing that. Yet another way. These two pieces of information are sort of contradicting each other. Not contradicting each other, but the second one is restricting even further for y. So I could say x is in -1 to +1. Y is in 0 to 1, and x squared plus y squared equals 1. I'm making all this up as I go, so please correct me if anybody out there sees this video after the fact, and please, at any point, correct me, let me know. I am just a hobbyist. I am trying to relearn mathematics, and I'm making up examples as I go. So, if you take the whole circle and think of it as points in space, then you have a graph, or an equation, or yeah, the graph of solutions of an equation. And once again, this has infinitely many points, but it includes ones like 0, 1. It includes the point 1, 0. It includes the point, if we remember back to trigonometry, it's going to include the points like root 3 over 2, comma 1/2. It's going to include the point root 2 over 2, root 2 over 2. It's going to include the negative points as well. So like x equals 0, y equals -1. This is an important part of what I'm trying to get at. X equals -1, y equals 0, and on and on and on. There are infinitely many solutions to that equation, and here and here and here, yellow and green are not sufficient contrast. Why don't we do, I don't know, cyan. It's still not great, but 0, 1 and 0, -1. We can see that the number 0, in some sense, would map to both 1 and -1. So, yeah, like, or we could say, like, 0 has two different values, 1 and -1. There's a way to make this rigorous as a function, that it's not mapping to the numbers 1 and -1, but it's mapping to the set, to a set of solutions. And that's where I think we get into Spivak's book. Like multilinear algebra and calculus. I don't know. I'm making stuff up. That's not correct. But like multi-valued functions can be thought of as like a number mapping to a set. And then can you do math and calculus on a graph as opposed to a function? There is a way to do calculus on graphs. And I think that is like the last chapters of this book, like calculus on manifolds. So let's try to read a little bit. Integration on chains. What the heck is a chain? Integration on manifolds. There we go. That's the stuff I'm looking for. Oof. Okay, integration. I want like differentiation and stuff. Easier stuff on manifolds. Now, most of the book is all about integration. All right, so this is very all over the place at the moment. But yeah, there are things like graphs, and there are things like charts and all sorts of interesting ideas in math. So the answer to that is a graph. And it's a set of points, which brings us to kind of some more questions than answers sometimes. What is a set? A set is literally just a collection of things. It's kind of like, you know what a set is, don't ask me. Stop asking annoying questions. Because like a set and a collection, they sound like the same word. It almost sounds recursive, but in some sense it's not, and I can't explain why. I'm not good enough yet at math to remember the precise definition of how a set is different than a collection. But it can be a collection of anything. It can be empty. It can have the letter A. It can have the letter A and the number 1. It can have you and me. It can have the English words you and me, which is different than the idea of you or me, or actual you and actual me. All of those are different things. So it's a collection of stuff. And math is mostly interested in sets of numbers, because there's a lot of interesting properties about numbers. And so, say that we have I don't know, what's a good example? Say that I've got a bunch of videos that I've uploaded to YouTube. Video 1, Video 2, Video 3, and Video 4. And your reaction can either be to hit the like button, or it could be to hit the dislike button, or it could be to like and subscribe, or it could be to dislike and subscribe, or it could be to what else? Do nothing. You could just click away, right? Those are all options of what you should do. And let's count. Let's see what happens. Maybe on the first video, it was terrible. Maybe the first video is bad because I need to practice. I need to keep practicing. So maybe you did nothing, or maybe you even hit the dislike button. Maybe that's what you did. And then if you watched the second video, maybe you liked it. Maybe with the third video, you liked and subscribed. And then maybe on the fourth video, well, you've already subscribed, so your reaction, from now on, you're always going to hit the like button, right? After you like and subscribe, every video from now on will always, forever, be to hit the like button for every video forever. So, here, this is a function from the space of the Math Hobbyist videos to the set of reactions. And of course there are more reactions. You can comment, you can like and subscribe and comment, you can share, you can comment something nice, or you could comment something mean. You could join the live stream, you could chat in the live stream or not chat in the live stream. So we need to model this in some way, and what we're doing is the simplification of just this model of maybe do nothing is going to be 0. Maybe like is L. Like and subscribe is LS. Dislike is D. Dislike and subscribe is DS. And What else? We're missing one, aren't we? Nope. Maybe that's it. I think that's it. There's 5 values in that space of reactions. And yeah, does that make sense? So your reaction to this video amongst all of these possible values is a function. It is a output given an input. What you're watching right now is an input, and you're having a reaction right now. And hopefully it is to like and subscribe. Or even better, you've already subscribed and you're just going to hit the like button again. Both of those are great reactions. All right, so that's an example of a function, and I think it's important to think of a function that is not numbers, that is not a normal math equation. Thinking about functions and math, we are looking for abstractions because we want to find patterns that hold true even when we're not talking about the real numbers with everything, with square root of 2 and with pi and everything. Like, how much of that is still true when we're only talking about fractions? Or, even better, the counting numbers. Right? How much of all this stuff is true when we're talking about a generic set? Any set of anything. An arbitrary set. You still with me? So as we keep moving to the right, we're going to get into weirder and weirder worlds towards topology. I don't think that's inaccurate to say. We're going to broaden and abstract our notion of what calculus means into weirder worlds. But we're going to start out somewhere nice, like the reals. And then, someday, we're also going to take a step back and find out that calculus should be in the complex numbers. It's so much more beautiful and lovely in the complex numbers. Everything is just nice and precise and neat and so much simpler, I think, from what I remember of classes. So these are different worlds, and I hope that makes sense. Any questions? Pause the video, drop a question right now. Go ahead, do it. All right, thanks for that. Let's move on. So let's focus on the real numbers for now, because that is what Taalman's book is going to focus on. What are some good examples of functions? Well, the simplest dang function is the one that, well, I don't even know if that's the simplest, but this is a very simple function. You have, here, one more thing I do like to always show. A function can be thought of as a machine. You give it a thing, and then it gives you another thing. It gives you something different. It does a bunch of stuff to it, and then it gives you another thing. The really lazy function, f, or maybe, I like to maybe call it e. E is a lazy son of a bitch. It will just give you back exactly what you gave it. Like, you give it something and it's like, no, I don't want it. You have it back. You can have it. Um, this is, or E is okay. I think we will actually see in context um, calculus, we will see it being called ID, like the identity function. It just returns the same thing. I don't think I'm making that up. Am I getting that wrong? ID. I don't know if that's true. Doesn't matter. Who cares? The point is that this is the lazy function. It will just give you back whatever you hand it. It's not even going to do anything. So something that's cool is that this function can be defined on anything. If you have a set, any set, including the math hobbyist videos, if I give you a math hobbyist video and you're watching it, somehow you return back, you give it back to me. I don't know what that would mean, but if it would be like we are going from one set to itself always. The worlds are up here from the original world to the new world, and everything in the original world is just kept exactly the same. That function exists for any set. That's easy to see. So that's an example of some mathematical statement that we can say about this super weird world, where it's hard to say many things, but we could definitely, from any set, I'm going to start using this notation now, from any set, we can also define another function that where if you give it a thing, it will always return the empty set. The empty set is it's like here we need to be talking about something like this. Yeah, so the empty set is the set with nothing in it. And a set can contain a set within it. Like, you can talk about my collection of math books right there and my collection of math books over there. They are two different collections, each which have things inside them. You can always create this as well. Like, you give a function a thing and it always returns you nothingness. That's a weird one to try to come up with. But anyways, I tried to start out with something familiar, and then we started going into the weird world. Let's come back to the nice world. Here, this is an identity function. Y equals x is the identity function in the real numbers. And so that's one simple example of a function. Another one is the function y equals 0. No matter what I give you, you always give me the same thing. You always give me the number 0. I give you x, you give me 0, no matter what. that is also a valid function. Now, yeah, here's a good point to try to introduce a fancy concept. Functions. I've come up with some annoying examples of functions. And okay, like here, this one, f of x equals 0. We can draw this. I mean, we literally can't list all the real numbers. That is a theorem that we'll get to at some point. But if they all were mapped to 0, what I'm trying to do is I'm trying to draw a diagram like this one. If they were all mapped to 0, then it's hard to, like, you can't say, like, what number did I give you in the first place? Like, if the function returns 0, you can't know what the function received in the first place, right? That is, for this number 0, which is in the real numbers, what is the preimage? Meaning, what are all of the numbers that map to 0? There might be infinite, and there are infinite in this case. What are all the numbers x that you, such that for any of these numbers, the function f, all that it returns the number 0 to you? What are all of those possible numbers? This is called the preimage of f. Okay, so this is in some sense opposite of this one. This other one preserves all information. It doesn't do anything to the world it was given. It returns you the same exact world. What about another function that looks like this? And I'm still thinking from an arbitrary set to itself. Maybe it has 3 things in it, which, for the sake of convenience, I'm going to call 1, 2, 3. But they can be 3 things, 3 points, 3 items. And it swaps them around, maybe. Like maybe 1 goes to 2, 2 goes to 3, and 3 goes to 1. Does that make sense? So f of the first thing in our weird world, which I want to avoid numbers here because I'm trying to show that this is something that's outside of the regular numbers. We have alpha, beta, and gamma. Whatever the heck they are. Alpha, beta, gamma, or x, y, z. This is a map. A map means a set of rules that it's a map is like kind of the arrows in these diagrams that I'm drawing. A map is the instructions for how to get a output for every input. Kind of like how to get from your house to the airport. You want a map for that. It's like the directions to get there. Do we still have the iPad on screen? We do. Good. And no chat, no questions yet. That's understandable. So here I created this function. F of alpha is beta. F of beta is gamma. And F of gamma is alpha. Okay? Well, then, if we have that, then what is the preimage of alpha? Well, there's only one thing that gives you alpha. It is gamma. This is the only map, the only directions that lead you to the output alpha. Here, F inverse beta equals the only input that returns beta is alpha. That's right here. And finally, the preimage of gamma is beta. Okay? Y'all with me? This stuff will be important as we move from applied calculus to more theoretical calculus. In both books, the yellow book and the blue book, the analysis book and the topology book, we will be talking about a lot of these concepts. The preimage of a function. Okay. All right, John, you're losing me. All right, so if we have arrows like this from a function to itself, we can also just walk backwards. We can like kind of trace our steps backwards to find where we started. And in contrast, we had this example where all of the arrows always return the number 0 for any x values. I shouldn't say xi, x2 because it's not countable, but let's move on. Okay, what's a less obvious or less I don't want to use the word obvious or trivial. What is or degenerative? What's a less degenerative example of a function that points where the multiple inputs point to the same output? What's a less annoying example? The one I like to show kids is a clock. Okay? I'm an American, so a clock in time only has 12 hours. 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 7, 8, 9, 10, 11, 12. Right? These are the numbers, not 0, 1 to 12. Okay? If it is if it is 12 o'clock, here, this is the fun example I like to show kids. I call it the skipping around the clock. Say that your favorite TV show is at 1 o'clock and it is currently 12 o'clock. And you, I like Pomodoro a little bit better than, let's use Pomodoro as an example. I always say taking naps. I've been saying taking a nap and you're too sleepy. I don't know. Okay, the way I've been telling kids is like, your favorite TV show is at 1 o'clock. It is 12 o'clock. You are sleepy. And need to take a nap. But you don't want to miss your favorite show. How long can you, what time should you set your alarm for? Like, how long should your timer be to wake up and watch the show? Well, obviously, you can set a 1 hour timer. And then 12 o'clock plus 1 hour is 1 o'clock. 12 o'clock plus 1 hour equals 1 o'clock. Okay, that works, but what if you're too sleepy for that? You need to sleep for more than 1 hour. Okay. Well, 12 o'clock plus 13 hours also equals 1 o'clock. In this formulation, the favorite show is at 1 o'clock a.m. and 1 o'clock p.m. I know it's a little absurd. It's a very silly question. It's a silly question, but it has some nice aspects about it. Okay, so these are two different additions that both add to the same number. So we can think of that as a function, and yeah. I'm mixing two different kind of lessons or ideas, but just to focus on what I've showed other people, it's like, okay, what if you needed to continually just keep taking the same length of a nap? Now I want to switch Pomodoro. Like, what if you want to do Pomodoro studying? And so you're going to set your Pomodoro timer for every 2 hours. And you start at the number 12, and you keep skipping and checking the TV show. Is your TV show on? No. Okay, take another nap or do another Pomodoro. Will you ever see your favorite show? No, you wouldn't, right? But what if you set 3-hour Pomodoros? Would you ever see your favorite show? No. I'm going to start writing these out. So if you took a 1-hour Pomodoro, yes, you win, but maybe you fail your homework assignment because you need to do at least 2 hours on it. Would you ever see your favorite show if you were doing 2-hour Pomodoros? At this point, we switch to these numbers, and then the kids or whoever, like, they start to see the pattern. They're like, okay, cool, I see what you're doing. You're doing, like, this clock math where anytime that you go beyond 12, it returns back. So this is modular arithmetic, really. And this is how I draw it for them. So I asked them what numbers might work, what numbers would work to be able to get to 1. Okay, it's none of those. And then sometimes kids do see it, that 5 will work. 12, 5, 10. 10 plus 5 is 15, which is equivalent to 3 in clock math. 3, 8, 1. Yeah, so then we got to 1 and it works. And then just out of curiosity, what if we kept going? Okay, eventually we're going to start cycling back and getting back to 12 o'clock. So taking 5-hour Pomodoro, 5-hour work blocks. 5-hour Pomodoros work. Would 6-hour Pomodoros work? Pretty clearly not. The only numbers would be 12 and 6. I'm going to start using parentheses instead of like an arrow to mean come back to the beginning. What about 7? All right, so the next number is 2. Next number is 9. 3. So 9 plus 7 is 16. Whoops. I'm a dummy. All right. 9 plus 7 is 16, which is 4 in the clock. 4 plus 7 is 11. 11 plus 7 is 8, which is on the clock, on an American clock, because we're in America. 7, 18... Oh, whoops, eraser. 6. 6 plus 7 is 13, which is the same as 1. So that one works. And then 8, 4, 3, plus 7, plus 7, plus 7. And then, 5 plus 7 is now going to be 12. So we come back to the beginning. So the parentheses, again, means come back to the beginning. So 7 works, 5 works, 1 works, and then you can show other ones don't work, but then 11 does work as well. 11 is cool because you can see it on the clock that each time it's stepping back one time, stepping back one number, and then you get to 1 eventually. So what does this have to do with calculus? kind of doesn't. It's more like number theory or algebra, and I just like number theory and algebra more, so I'm using this example. But it does have something to do with calculus. Why am I bringing it up here? The idea here is that there are multiple numbers that can add to 1. Or like, yeah, 1 o'clock. How do you make that precise? There are 2 times in the day that it is 1 o'clock. That the number that your clock is pointing. There are many times in your life. There are many times in your life that your clock is pointing to the number 1. There's not just one time in your life. There are 2 times every day that the hour hand points to 1 o'clock. So this is an example of a function. F is not F is not 1 to 1, which fancy talk is going to be injective. There are functions where a function always satisfies the vertical line test, if we're thinking of it that way, but then a injective function also has a horizontal line test as well. For every y value, there exists a unique x such that f of x equals y. There's one x value that maps to one y value, 1 to 1. This function is 1 to 1. Okay, here's another stupid example. If you get blackout drunk and you wake up in one place, do you know what you did last night? If you can retrace your steps, and if there's some way for you to retrace your steps and know exactly what you did last night, then I don't know, the party you were at or your life situation or whatever is 1 to 1. Like every y value has one x value. Maybe I should give that one a different color so I can say that it, this channel is very immature. I apologize. So these are like double-sided arrows. Every input has one output. Every output has one input. Is a injective function. Let's come down here. So that's one. We're talking about the zoo of functions. We found one that is great. There's one type called a injective function. 1 to 1. Double-sided arrows. There's another kind called a surjective function, which is onto. What does that mean? Okay. Try to make up examples. let's say I don't know. The parabola. A parabola, it satisfies a vertical line test. So it is a function. It does not satisfy a horizontal line test. So it is not injective. It is not injective. It also is not surjective, because if you check for every y value, there has to be a value for the function at that spot. That doesn't, I don't know why I drew it exactly those 2 points, but there does not exist, there is no x such that f of x, which is x squared, equals negative 1. So maybe this point right here is negative 1. So even though negative 1 is in the real numbers, from f being from the real numbers to the real numbers, even though is kind of the wrong term to use there, but it's kind of accurate. I don't know. Negative 1 is in the real numbers, and if you consider f as a function from the reals to all of the reals, then f is not surjective. For the sake of seeing what we're doing, I'm talking about the function x squared. X squared, the function x squared is not surjective because there is no value that maps to the value negative 1. So we were talking about some interesting examples before, like there are 2 different lazy functions, one that just returns the exact same thing you gave it. This one is one-to-one and onto. Every value on the right-hand side has a value to begin with. That's a lazy function. But then there's also this other lazy function where everything gets mapped to a single value, a single constant. So from alpha, beta, gamma to, again, alpha, beta, gamma, where f of anything equals beta. This one is not, this is neither injective nor surjective. And the reason that I'm bringing it up is there is no x such that f of x equals alpha. Nothing maps to alpha and nothing maps to gamma. There are these like lonely Yeah, there are these lonely, neglected dots in the right-hand side of this function that, you know, weren't invited to the party or something. I don't know. Right? So therefore, it is not surjective. That's what I'm trying to get to. This function is not surjective. And here's another example of something that is not surjective. Okay. Well, I keep drawing this kind of thing from this to this. And I'm using the example of x squared right now. We know that this is not surjective, as I just showed. But it has a sibling from R to R plus. What is R plus? R plus is the set of all real numbers from 0 to infinity. The set of all non-negative real numbers. This one is surjective. This one is not surjective. I'm going to stop writing out surjective because that's a scary word. And I'm going to start using the other term that I think is easier for me to remember. Onto is another synonym for surjective or surjectivity. A function that is onto means every value is every value is put onto is there's an arrow onto every value in the second world. Okay, so this is just a slight modification of that same function x squared. And what we did is we changed our consideration and we clarified okay, well, you know what I meant. I didn't mean all real numbers. I meant the positive or the non-negative real numbers. And then you say, aha, all right, well, in that case, yes, that function x squared is onto. And then you get annoyed at that snarky person or annoying person. So, what do I want to go to next? What I'm trying to say is that every function is always a function from one set to another set. And the world that you start from is the domain, and the world that you go to is called the codomain. It's closely related to the range, which is the range is all values that are in the codomain, that are mapped to the subset of B that is onto, where f of A to R is onto. Where R is part of the bigger world B. Okay, so that is a strange concept. I'm getting a little weird. I'm getting away from engineering. Let's figure out how to throw a baseball and how far we can throw it. Any questions? What's going on? All right, I promise that this is a calculus stream, a calculus lecture. But I am defining a lot of things in terms of topology or abstract functions. And that's partly motivated because we had a great question from somebody. What is the name of an equation that is not a function, like the letter C? It is a graph or an equation or a set of solutions to an equation. Okay. And then I think that there are even weirder answers to that question. There are even stranger worlds, even stranger answers. If we start looking at this book. If we start looking at this book, or another one that I don't have on me, the world gets even stranger, and we're not talking about sets, we're talking about categories, and that's an even stranger answer. There are even stranger answers to that question if we start another small, scary book. The smaller the book, the scarier they are. And while I do have it, I just want to show that, because it's fun to show to the camera. As we get into more complex math, hey, the reason I'm drawing so many dang arrows everywhere is that math gets more and more arrowy. You just start drawing arrows everywhere, and you just start drawing diagrams. These are things called commutative diagrams, and they contain a lot of information in them, but they're just kind of cool looking. If you ask me, they're just cool. Like, what the heck? What are all these symbols? Like, every now and then I open this book just to laugh and be like, I'm not smart enough for this sort of thing. Like, what are all these symbols? What could this possibly mean? What are these crazy diagrams? We'll get there someday. What's up? Hey, Alok is here. How are you, man? Hello, I'm here, and thank you so much for this Calculus Live. Can you give me a quick recap? It's a weird calculus lecture, dude. This is a weird calculus lecture. Basically, I'm defining functions. That's the short answer. And it's motivated by a viewer asked, what is the name of an equation that's not a function, like the letter C? The short answer is a graph, but what we're getting to is the ideas of what a function is. Like, every input should have one output. And then I started talking about the different types of functions that one can have. An injective function says that for every output there's one input, and for every then there's the other concept called surjective. And in terms of injective, an example is this one that I like to give with kids, like a clock. There are many times of your life that the clock is going to be at the hour hand is pointing to 1. There twice a day, the hour hand is going to be pointing exactly at 1. So there's not only one time in the day where the value of the clock is 1. So that is not injective. Like your clock, in a sense, is not injective. In American clocks, in American time, 1 o'clock can mean 2 different times of the day. In European clocks and time, there is only 1 o'clock. I've never thought of it this way. I like it, though. I like it. American time is injective. Is not injective. European time, European hours, really, is injective. There are 2 times in the day that it's 1 o'clock in America. There's only 1 time in the day that it's 1 o'clock in Europe. That's, I don't know, that's a silly example, but it works. That might stick in your head, you know. Injective is 1-to-1. Surjective means onto. Are there any x values such that x squared plus, or x squared equals -1? No. There are no values, x, that map to -1. So f of x equals x squared is not surjective if you think of it as from the reals to the reals, but it is surjective if you're considering it as the reals to the positive real numbers. Okay? This one is onto, the other one is not. Every value in the codomain is mapped to from the domain. Another way to say that is the codomain equals the range of the function. That's another way to put it. Even before all of this, I gave a little introduction in this lecture about the books that we're going to work through. I showed some of the books: Taalman, Rosenlicht, Tenenbaum, Gamelin. Taalman is first year introduction to calculus. Rosenlicht is calculus for math majors. Tenenbaum is differential equations for engineers and mathematicians. And then Gamelin is topology, which is really only for mathematicians, sort of. And so some of these ideas, like really emphasizing surjectivity, injectivity, and some of these weird examples of sets that are not numbers and functions that are not on numbers, that becomes more important in the harder books. Yeah, especially topology, where everything just gets really weird. So we're defining the zoo of functions: injective, surjective. What else am I looking for? We can start getting a little bit more clear and start talking about piecewise functions. Eventually we're going to talk about continuous functions. And later on we're going to talk about differentiable functions. This stuff is calculus. This stuff is talking about like really understanding smoothness in an equation, in a graph. For example, y equals the absolute value of x is continuous, but it is not differentiable at the point 0 because it's sharp. A differentiable or a function is differentiable at a point. Like we always talk about differentiability at a point, as opposed to and then you say that a function is differentiable everywhere, or it is differentiable if it's differentiable at every point. But both of these ideas are very important, and topology really studies continuity in abstract spaces. Yeah. Differentiability, continuity. I don't know if there's any other types of functions that I'm missing right now, but this is where we're going. And to get there, we need to understand some of these previous examples. So let's jump into it. Let's get some problems. Let's do some problems. I think I briefly looked and I saw, like, great, okay, Taalman also starts exactly at the same thing, or at the same ideas, and so do the other books. Like, all of these in chapter 1, section 1 of all of these books, they all start at functions the exact same way that I am. So that makes me feel good about myself. I apologize. Do I have my feet on camera? Oh my god. Okay, you don't have the iPad this whole time. Come on, y'all. You're not helping me out? Come on. I thought you were still paying attention. I probably lost you, Alok. I apologize. Nobody mentioned it, though. Come on. All right, so I was writing a lot of stuff and nobody pointed it out, that they couldn't see what the hell I was writing. But this is the zoo of functions that we're going to try to define and create, and we're going to get weirder and weirder ones. Especially in topology. Nope, I am here. Okay, great. Well, I'm glad. But, yeah, so if it ever seems like I'm writing a lot of stuff and you don't see the iPad, just mention it, like, oh, no iPad or something. I don't even remember when I think I showed the category theory book. That's what happened. I showed the category theory book. No worries. Yeah, you're good. I'm sorry about that. My fault. All right. Let's do some problems. Math is about solving problems, not ranting at a camera. Taalman. From here on, I'm going to assume Taalman did more work than Kohn, because their name is first on the book. So I'm going to credit Taalman more, and I'm always just going to say Taalman when I really mean Taalman and Kohn. So section 0.1 is on functions and graphs. And I haven't read it, but I'm glad that they define functions and graphs, and they contrast the two, which I think matches exactly my answer to the viewer who asked, what's the name of something that's not a function? Like, this person is saying functions different from graphs. Remember, functions are different than graphs. Close, but different. Okay. I love this. Taalman always says, problem 0. Read the section and make your own summary of the material. Like, what a troll. I love it. Like, every single problem set in this book, there's always problem 0. Take some damn notes. Do this. Like, problem 0, actually read the section and make your own summary. I love it. I think that that's a great thing to explicitly assign and say to the reader. Like, don't forget to actually take your own notes and make your own summary. Like, summarize this in your own words. In a sense, that's what I'm trying to do up here in this whole long opening of this section of this live stream. I'm trying to put functions into my own words, including weird examples like YouTube videos and things, because it solidifies your understanding. It like really helps you understand things in your own words. I'm going to skip that one because, yeah, I'll do that on my own time. All right, so this asks, true or false? Determine whether each of the statements that follow is true or false. If a statement is true, if true, why? If false, provide a counterexample. A, true or false? Functions are the same as equations. No. False. X plus 2y equals 3 is an equation, and it can be thought of as a function of y or a function of x. I think that that's a good counterexample. That's one counterexample. Another is that, like I was doing earlier, here is an equation for a circle, but that is not a function. So even if you can write down an equation, where am I going with that? I don't know. That's an equation. Any questions? That's an equation. Let's move on. And it's not a function. The domain of every function is a subset. I like this question because it depends on what she means. I think Taalman, I don't know their pronouns. I should keep saying they until I look it up. The domain of every function is a subset of R. I think that in this book, in their definition, they define the abstract definition of a function. So it is not... We are not assuming everything in the real numbers, I think. So, in theory, definition 0.1 of functions. I'm going to write this out precisely. A function f from a set A to a set B is an assignment. I like that. Okay, an assignment f that associates okay. I like this definition of a function. I think it's great. I think it's beautiful. I think that this is a beautiful book. A function f from a set A to a set B is an assignment f that associates to each element x of the domain set A exactly one element f of x of the codomain or target set B. Okay, there's an important okay. Yeah, so in this book, I think we do assume everywhere that we're talking about real numbers. But technically, in this definition, I think that they are not. They don't say that. What I'm checking on right now that I'm looking for is, do they define a set? That's a little challenging. It's a little tough to try to define a set in a way that doesn't cause all sorts of problems. So is it in the appendix? And they don't have any note about that. They don't note that. They do not note that there's a weirder world. And that makes sense. I just wonder if anywhere in this book they try to define what a set is. Like, even just the general saying that a set is a collection of objects, a collection of numbers, or a collection of things. Yeah, they just avoid it. They just straight up avoid it. That's cool. Hey, how's it going, Math Spellbook? How are you? Good to see you. We're gonna begin talking calculus. We're talking calculus today. I'm defining the zoo of functions is how I called it. And yeah, it looks like this book just assumes everything is in the real numbers. The first definition that Taalman writes is not assuming real numbers. It is talking about a generic arbitrary set, which is cool. Someone, hi, how's it going? Someone, new viewer, I think. How are you? How's it going? I'm working through some calculus. I'm starting a calculus book today. Now we have definition 0.2, the domain and range of a function. So I want to write out some of these things precisely so that y'all see what an actual mathematician would say. The math major's rite of passage, cool. You mean calculus? Oh, calculus is, yeah. It's everybody's rite of passage, like any STEM major's rite of passage. If F, or do you mean trying to define a set? I would say that that's a rite of passage too. If F is a function between unspecified Yeah, this is interesting. Okay. So this is what I did earlier on my own when I was ad-libbing all of this introduction to functions. You need to define a function being a mapping or a rule or an assignment. I like the term assignment, from some set A to some set B, and you call A the domain, you call B the codomain or target. I haven't heard the term target before, but I like it. From the domain to the codomain, and then the range is the part of the codomain that it can attain. The range is a subset of the codomain. And then I find it's weird that they redefine domain of F. It's like we're talking in this definition about an unspecified function, like if we just write down f of x equals x squared minus 1 or whatever, that we are talking about, or maybe a better example is f of x equals the square root of x. I think Taalman is just trying to say, I'm not going to bother always writing down that f is going from 0 to infinity to 0 to infinity. I don't want to, like, don't be a smart ass. We all know what I mean. Square root of x is going to be from the positive real numbers to the positive real numbers and 0. So the domain of f, in this case, the domain of the square root function is the largest subset of the real numbers where the function is defined. I don't care about thinking of the part of the real numbers where the function is not defined. Like, that's my mental model. But what's odd to me is that it's like here they are defining domain and then they're defining it differently than domain right here, like a moment ago. So that's just a little strange pedagogically to me, but maybe, like, it kind of makes sense. I don't know. And then just for fun, I promise you all I did not pre-read this. Definition 0.3. I literally did not pre-read this. The graph of a function. So I knew it when this audience member asked, what is something that's not a function? And I was like, it's a graph. And that's different than a function. And it's important to realize that they're different. Range and codomain are different. They just are. They're just different. Don't think of them as the same. Like, often you do restrict and say the same thing that's like, I don't care about the numbers that it doesn't map to. Let's only think about the domain to the range. And then that's a valid point. But you want to think of functions as the range being different than the codomain. It is worth thinking of a codomain, at least as you get to more complex math. The quote-unquote graph of I'm going to start using fn to mean function. F is the collection of ordered pairs. Yeah, I should have written this like a little bit more explicitly. I love this. I started writing it earlier, but I didn't put it so cleanly, for which I thought of it too, because this is like a nice definition of functions on an arbitrary set, for which x is in the domain of f. In set notation, we can write graph of f equals all of the ordered points x and f of x such that x is in the domain of f. Okay. This is actually slightly different because we're talking about the graph of a function, right? That's in contrast to the graph of an equation. because there can be a graph of an equation like x squared plus y squared equals 1. What I was drawing out earlier is that this has, you know, 0, 1. It also has 0, minus 1. It also has 1, comma 0, and it also has minus 1, comma 0, and infinitely many more. But these are four solutions. These are four coordinates or 4 points in the two-dimensional space R2. In general, the graph of a function f from a to b, the graph, or I did it again, the graph of a function, but the graph of an equation is going to be a collection of ordered points where the first coordinate is in A and the second coordinate is in B. And it's a collection of all of these points. Yeah. So earlier we were talking about the graph of an equation, and we can see that this is not a function of x because we have 0 positive 1 and 0 minus 1. And we also have, it's not a function of y either because we have y equals 0, x equals 1, and x equals minus 1. I hope that makes sense. Yeah, so what's going on? Oh, the math major's rite of passage, real analysis. Yeah, real analysis is the dream crusher. Right? Yeah. Real analysis is the rite of passage, I think, it is the hardest class in undergraduate math, or really, to me, I don't know. For me, it's the hardest form of math for a lot of people. Calculus on Manifolds, Introduction to Analysis, these are going to be our analysis books. Yeah, so range is different than codomain. Range is a subset of the codomain for any function a to b. And the subset can be equal. They can be the same dang subset. They can be the same thing, but they're not always the same thing. Neat. Okay, so we're talking graphs. And then look at this. Theorem 0.4, the vertical line test. Yeah. I'm going to skip that one. I'll write it, though. Theorem 0.4, vertical line test. ... Definition 0.5, a 1-to-1 function. Look at how smart I am, y'all. I did the same thing. I thought, okay, if I'm going to teach calculus, I got to start out talking about 1-to-1 functions. A function f is 1-to-1. I'm going to use shorthand, okay? So don't do that. Write out the word 1-2-1. If for all a and b in the domain of f, if a is different than b, then f of A is different than f of B. This is a way cleaner, way more precise way to write what I was saying earlier. Because what I was saying earlier was talking about like a horizontal line test, and it was talking about two separate points can't map to the same point. This is neater. This is like two different points. Yeah, well, I don't know. It's just a nicer way to write it down. I would be so happy if the next page has a horizontal line test theorem. Oh, it doesn't. No, I thought it would. Maybe it's an exercise. I just really like how this book clearly separates examples versus definitions versus theorems. Is it in the proofs? Yeah. Yeah. A horizontal line test. Like what I did over here. I was defining a one-to-one function and talking about a horizontal line test. And that is problem 91. Problem 91. Use definition 0.5, the one that we just wrote, to prove that a function is one-to-one if and only if its graph passes the horizontal line test. That's cool. No, bijective is not. Yeah. One-to-one is the same as injective. Yeah. One-to-one is injective. Surjective is onto. I like the term onto and one-to-one. But then fancier books will use injective and surjective and bijective. But this is... It's so cool, because like this book avoids those scary terms, but it still introduces the exact same concepts. And mathematicians use the same concepts too. It's just when they want to feel better about themselves, they use the scary words. And when they are not trying to feel good about themselves, they just use one-to-one and onto. Cool. All right, so we got a little bit of theory motivated by answering this question. The domain of every function is a subset of the real numbers. I'm going to say false because we defined functions about sets, and then we started always saying if f is defined on the real numbers, then blah, blah, blah. Here, this is not at all talking about the real numbers. This definition of a graph is abstract. This is an abstract definition of a graph. And so is this. So here, yeah, this is like a very precisely stated, like if the function is defined on the real numbers, then the domain of f is all of the real numbers where f of x is defined. But the actual definition of a function is on this mysterious thing, set A, that Taalman just conveniently avoids defining. They're just like, I'm just not gonna say what that is, a set. A set is a collection of things. It's a list of things. It's potentially infinite, but it's a collection, and don't ask any more questions. So I'm going to say false. we have, so Taalman asked for a good counterexample, and I'm going to give the counterexample of that I gave earlier of my YouTube videos, okay? All right, so if we have a YouTube video, your reactions can be to like and subscribe. Your reaction could be to like. Your reaction could be to dislike. Your reaction could be to dislike and subscribe. Or your reaction could be to do nothing and click away and do nothing. So, for everybody here watching, the first YouTube video of mine that you see, you're going to like and subscribe. And then from then on, every other video that you see, that you watch, you're going to like. Okay? So this is an example of a function that is not on the real numbers. Okay? It's your reaction to watching this video right now is either to like and subscribe if it's the first time you've seen one, and it's to like if it's not the first time you've seen one. Does that make sense? ... forever. It is not onto, because you will never dislike any of my videos. You will also never dislike and subscribe to any of my videos. And you will also never do nothing with my videos. It's like, this is like subliminal messaging. I'm just like, you shall never do nothing. You shall always like and subscribe or like. Thanks for reminding me to like the stream. Thanks, man. Yeah, no, I have to remind, like, and I get it. I'm not like being passive aggressive right now or anything. You have to remind your viewers to do it, because otherwise, it just takes a moment to do it. But anyways, there is a great, beautiful function. The function from the Math Hobbyist videos, from the Math Hobbyist channel, to the set of reactions. Okay? I think that that's a cool example. All right? So in this, the Math Hobbyist is in the space of YouTube videos. And so we're restricting the function. We can either think of the Math Hobbyist from all YouTube videos to reactions, or we could think of it as the restriction to the Math Hobbyist to reactions. And we could analyze which of these are one-to-one, which of these are onto, which ones of these are defined, which ones are functions, which ones aren't, etc. I hope that makes sense. So there's an example of something that's of a function that is not defined on the real numbers. And I hope that that makes sense. Like, I hope that these silly, weird examples stick, in your head. Like, functions don't have to be on numbers. They can be on other things. A less annoying example is another function from the complex numbers to, I don't know, the real numbers or something. Like, maybe you have a complex number, a plus bi, and you just throw away the imaginary part of that number. Or maybe a little more interesting, like you only take the coefficient of the imaginary part and you project that to the real numbers. Yeah. So everyone is here for the maths. I think so, right? Everyone here is for the maths. Thanks, y'all. And I appreciate it for, I appreciate you for posting this to the Math Streams channel. I'm too lazy about it. I think that's really cool. I think you're the only one in my Discord at the moment who cares about those math streams, about that Math Streams channel, but thank you. Here's a good moment to say, anybody who wants to, if you want to join the Discord, I do have a Discord. It is a blend of classical guitar and mathematics. I think discord.jcpractices definitely works. I don't remember if I've set this one up yet, but it's the same, or it should be the same. discord.themathhobbyist.com. If it doesn't work now, it will soon, by the time people watch this video after the fact. Yeah. Cool. So let's keep moving. Let's solve some actual problems. I'm doing problem 1 from Taalman. Problem 1C asks, true or false? The function that for each x has output f of x equals 1 is a one-to-one function. So, just rewriting for brevity and summarization and sticking in my head better, f of x equals 1 is one-to-one, is false. Let's make it very clear. F of 0 equals 1 and f of 0 and maybe f of 1 is 1 and 0 does not equal 1. There are two different points that map to the same output. So it is not one-to-one. One D. Okay, yeah, here we're going to get into a new concept I haven't talked about yet, but that's fine. Every global maximum of a function is also a local maximum. I thought I misread that. That is true. So explain why is how they put it, right? If true, why? We need to know what a global maximum is as opposed to a local maximum. Let me see if I can remember and summarize in my own words. A global max, I mean, I know what the idea is, but how do I write it down precisely? A global maximum is a point x such that f of x is greater than, or let's say x naught, such that f of x naught is greater than or equal to f of x for all x. A local maximum is going to be x naught such that there exists a ball around x naught that there exists a a neighborhood A, I'm going to use delta. There exists a delta greater than 0 Okay, so what the hell did I just write? We're saying that there's some point x naught and some neighborhood around it. I think that these should be open. I don't know. Do they need to be open? Does it need to be an open neighborhood? I don't remember. There needs to be some space around that point where the function is at a maximum for some neighborhood around it, even if later on the function gets bigger, at least within this little neighborhood, that point is the maximum point of the function. It's like a little piece of the function where it's the maximum point. So that's my summarization. Let's see how Taalman defines it. This is good practice to actually try my own and see how wrong I was or how imprecise I was. Let's see what notation he or she uses. Let's find out. Let's just, ow, my leg, ow, I hurt my leg, ow, ow, shoot. I was just, that was a lot. Okay, I was kicking up my feet too long on the table. I'm getting old. Okay. Okay, I like it. So they don't use the word definition here in this table. They just say, here are some terms we're going to use. But they don't call it a definition. They call this vocabulary. This is such a cool book. I just think it's great. Well, no, it does say definition. So I guess I take it back. But definition and behavior. But this definition's a little squishy. Okay. We have the definition of a root, which I'll add later if we need it. We have the definition of a y-intercept. We have the definition of f being positive. Ooh, neat. Okay, yeah. All right. So f positive, f increasing. Neat. F is increasing, monotonically increasing, etc. Yeah, they don't use monotonically increasing or defining monotonic at all, and that's fine. F, local maximum. at x equals c. This is the one that we want, and then there's some more. So the definition of f having a local maximum is that f of c is greater than f of x for all x near x equals c. I like it. And then the image that you should remember is that the graph has a relative, quote-unquote, hilltop at x equals c. Okay, I like the notation x equals c. Why not? I used x naught as opposed to x, like a specific x as opposed to all of them, but c works too. And I drew a little hilltop as well. So that makes sense. Like, it's like if you look at all the numbers near that number, if you look at everything near it, then there's a hilltop. That in their notation, f of c is greater than. Is it greater than or equal to? Yes. Okay, that was a question I was going to have. Greater than or equal to f of x for all x near that point, near the point c. Okay. Maybe it's just because I'm a math major, but I'm so used. I like x naught as opposed to c because it reminds you that it's an input to the function as opposed to an output. C, the letter c to me sounds like a constant. I think of the function f of x equals c. It's that one lazy function that will always return the same output no matter what you give it. Whereas, so I think of c being this value in a constant function, whereas Taalman means c to be in the domain, a specific input to the function. So I like to think about style. Like, sorry, y'all. I like to think about why did this author use this symbol? Why did this author use this definition as opposed to this other definition? Why did they use a Greek letter as opposed to an ASCII letter? I don't know. Like, I like thinking style because it's important. Like, clarity is important. You will not see me write where I did write it earlier and I felt bad about it. I wrote it somewhere, but I will generally not write these fancy symbols for all there exists, and there exists a unique. I think that those symbols are too stylish. Like, it's an ugly style because it makes everything look like hieroglyphics and it's not worth it. Like, math, you should write math in full sentences. You should write math as English sentences and remember that math is writing. There exists. I will usually write out these phrases as opposed to using the symbol. But sometimes I'll be lazy. Call me out if I'm using these symbols too much. But yeah, that's a style thing. Some books will use way more of those symbols, and they want to show off how smart they are, and they want to use these scary, fancy symbols or this scary terminology like injective as opposed to one to one. Like, that's all style, and that matters to me. It matters a lot to me. If you're a programmer, I think it should matter to you too. And you should not impose the idea that there can be one true style. Okay? There can be multiple valid, interesting styles. There's my little rant about style guides in programming. All right, so every global maximum is also a local maximum. I don't know, I think that's just clear. If f of x is... If f of x naught is greater than or equal to f of x for all x, then f of x naught is also greater than or equal to f of x for nearby, for neighboring x. For neighbors, for the neighbors of x within this little neighborhood. Moving on. 1e. Ooh, we got average rate of change coming up too. Neat. Already in section 0 about functions. That I wouldn't have expected that, but I like it. Okay. Every local minimum of a function. I do like fn though for function. Sue me. Just stylistically, I like fn. Every local minimum of a function, and from now on, I'm also going to start using min instead of minimum. Every local minimum of a function is also a global minimum. All right, so at first glance, it seems like they're just asking the exact same question, just rephrased for minimums instead of maximums. But that's not the case, because in part E, we're talking about local minimums are local somethings are global somethings. Whereas in part D, it was every global something is a local something. I think that's clearly not true. That's false. What's a good example? The function that looks like this. Which I think we could figure out how to get it, but we could probably just pull out our other book on algebra and figure out what that function is, but I think it's some cubic. It's a cubic with 3 roots. The 3 roots could be x plus 1 would be the leftmost root, x being the middle one, the middle root, and then x minus 1 is going to give us the rightmost root. X cubed minus x. I think that that is the same as that graph. So I'm thinking, restating everything. I thought of a graph and I tried to figure out what the function is that represents that graph. They're different. The graph is the drawing, the function is the rule that draws a drawing. I think that that's right. This one is going to have three roots. It's going to have a local minimum right there. That's a local minimum. For all the neighbors of this function until right about there, for all the neighbors of that function, this is a minimum. But beyond that point, further out to the left, it is not a minimum. There are smaller values. There are other examples I could come up with, probably. I mean, even easier, or even smaller of an example. Let's take the other lazy function, y equals x. You just return everything exactly what you gave it, or something. Within this neighborhood, oh wait, no, that's not going to work. Yeah, I'm going to stick with this. I think it's the best example I'm coming up with at the moment. 1E, 1F. We're almost done. We have H, G and H left to go. The graph of a function can never cross one of its asymptotes. I think that's true. That's like the definition of what an asymptote is. Right? Recall that an asymptote is this dotted line in a graph where you have a function where the graph doesn't cross that dotted line. It can be a vertical asymptote, which means that when I don't have, yeah, all right. There is no, wait, I don't know if I can write this clearly right now. Spot is a vertical asymptote. It means like f of x naught is undefined and maybe there is no maxima in I don't know if I can define an asymptote, but this is roughly what I'm capturing in this one. Like, there is no maxima, which also is another way of saying that f of x naught tends to infinity or to minus infinity as x tends to the point x naught. That's going to be a future section. I can just tell based on the organization of the book, this stuff I'm writing here are limits. And that's probably the next section. What is Taalman's definition of an asymptote? Average rate of change. What is an asymptote? I don't see a definition of an asymptote in this. Oh. Yeah, sometimes a graph gets closer and closer to a horizontal or vertical line or asymptote. In chapter 1, we will define asymptotes precisely using limits. Look at me. This is not pre-read. I'm telling you, not pre-read. I was going to say, it's kind of hard to define an asymptote without a limit. I'm trying to define it with a limit, but okay, for now we will use the following definition. And I also said, you can think of it literally as a spot of the graph where the function doesn't cross a line. For now, we will use the following definition. A line L is an asymptote of a function f if the difference between the graph of L and the graph of f gets as small as we want as either x or y increases in magnitude. Huh. Notice that a graph can cross one of its horizontal asymptotes. The preceding graph above does so at the point 0, 1. This is just one of the reasons that we are avoiding using the overly loose definition of an asymptote that you may have heard in previous courses. An asymptote is a line that the graph gets infinitely close to but never reaches. Interesting. Okay, so that's a great counterexample to what I was thinking, I guess. So here, they don't draw the, or they don't state what function this is. They just draw the graph. And I don't remember how to write down this function, but I guess it doesn't matter. This is a function that has a horizontal asymptote it has horizontal and vertical asymptotes. But it does cross the horizontal line right there with that piece of the function. So they say it is possible for a function to cross a horizontal asymptote. Okay. The graph of a function can never cross one of its asymptotes. Did they state vertical? Nope. True or false, the graph of a function can never cross one of its asymptotes. False. example in the section. Crosses a vertical asymptote. Cool. Now, I think if the question were rephrased as the graph of a function can never cross one of its vertical asymptotes, I think that is true. Because, oh wait, no. I think that you can define a function. Like, what do you mean by cross? I believe that this is the function 1 over x, and it has a vertical asymptote at x equals 0. But what happens if you define the function piecewise? Wait. If x is negative, then it tends to negative infinity. This function is undefined at 0, but you can create a separate function f of x equals 1 over x if x is not 0, and you can define it piecewise as 0 if x is 0. So this just has two separate rules. It's like, well, if x is not 0, we use 1 over x. If x is 0, we just define it at 0. Does this cross one of its vertical asymptotes? Maybe. I don't know. What do you mean by cross? So that's just a twist of that question that makes it interesting. 1G. Average rates of change can be thought of as slopes. Okay, average rate of change between 2 points. I think the average rate of change can be thought of as the slope of what we call the secant line that connects 2 points. If I remember correctly, I think that that's what we're looking at. Let's get the definition. This is a lot of math, y'all. Oh my god, it's already 12:40. I've been doing a lot of math over here. This is fun. I like this stream. It just like encourages me to do math all day when I have the free time, at least. Definition 0.6. Average rate of change Y'all enjoying this? Maybe just ASMR, just like background noise, like somebody else studying. The average rate of change of a function f on an interval AB is the slope of the line from A comma A FA to B comma FB Cool. Yeah, it's pretty much exactly what I thought it was going to be. Yep, background noise. Heck yeah. Background noise is the goal. Thank you for hanging out and encouraging me, even if I'm just talking out loud. And, it's encouraging me to do more math, I think. How tough was real analysis for you? It was fairly tough. I mean, I got through it. I didn't have to retake it, but I had to work a lot harder. I had to work a lot harder in real analysis. Epsilon delta proofs, it just doesn't come as naturally, or I don't know, it's just fiddly and just kind of ugly and doesn't feel as structured and clean and whatever as algebra. Yeah. Yeah, real analysis is hard. It just is. Okay, average rate of change is that stuff. And, well, guess what? It is exactly in the definition. Average rates of change can be thought of as slopes. Yes, it's in your own definition. True. In definition. Okay, 1G. I think we have one last one, and then we're done for today. 1H. I hate it when... Well, I don't hate it, but, it's misleading when I see that there's, 100 problems in this section, but then some of them have, 10 sub-problems, A through H. That's a little disingenuous. True or false? A function can have different average rates of change on different intervals. Okay. To prove this, we just need one example. The parabola x squared, I see really easily that the slope of the line, let's use a different color. The slope of the line connecting the interval 0 to 1 is different than the average rate of change connecting the points -1 and +1. Right? Okay, done. Thanks everybody for watching. I doubt anybody after the fact is going to see this, but thanks to everybody who tuned in today. Thank you. It's really fun to have some company as I practice math and just work some problems. We finished problem 1 from Taalman. So we're on our way. We're going to solve every calculus problem. All right. 1 down. Thank you all for watching. This was fun. Have a beautiful, wonderful day. Like and subscribe. I really appreciate it very much. And yeah, go do something awesome. Go study some math or learn an instrument or something. All right. Bye, everyone. Bye.